Okay, so last time we have defined what it means that the function of two variables is differentiable, and also a function of more than two variables is differentiable. So maybe just to remind you, I write once more the definition on the blackboard. So f is differentiable if so the definition is okay, so we look at what we called last time delta set. So this is f of x plus delta x, y plus delta y minus f of x y. And if we can write this as the partial derivative of f with respect to x times delta x plus the partial derivative of f with respect to y times delta y plus a function epsilon 1 which depends on delta x and delta y times delta x plus a function epsilon 2 which also depends on delta x and delta y times delta y, where epsilon 1 and epsilon 2 both tend to 0 as delta x delta y tends to 0 0. So this is what differentiability means for a function of two variables. If you look at this definition, maybe once more, it looks pretty different from the definition we have given last semester for a function of one variable. But actually last semester we have discussed, or we had a similar condition which we discussed when we proved the chain rule. And as I have explained last time, so we take this equivalent definition of differentiability of a function of one variable, which is similar to this one, in order to extend the definition to functions of two variables. Now, we also saw last time that it's not true that f is differentiable if and only if the partial derivatives exist. This is not enough. For differentiability, of course, what you need, you see this here, is the existence of the partial derivatives. But the inverse is not necessarily true. So last time we showed already that if the partial derivatives both exist and are continuous, then f is differentiable. And this assumption here, continuous, cannot be dropped. So it's not just enough to assume that the partial derivatives exist. Okay, so differentiability, once more, for functions of two variables is not equivalent to saying that the two partial derivatives exist. Okay. The reason I explained already last time, the reason why we do not expect that differentiability for functions of two variables can be defined that easy is kind of similar to the problem of the limit. We saw already for the limit that for a function of two variables, okay, it's not enough that you just consider limits in certain directions, approaching along the x-axis and approaching along the y-axis. Even so, the limit exists in both directions and is equal. And this equal, this does not necessarily mean that the limit of the original function exists, because you have more directions. And those two derivatives here are the derivatives of the function f at a given point with respect to two specific directions. And one of the aims today is to define kind of partial derivatives, but in more directions, not just in the. So this is more or less the direction of the x-axis, and this is the direction of the y-axis. And we wanna one of the goals today is to define partial derivatives in more than just those two specific directions here. Okay, but before we can do so, we have to discuss the chain rule for functions of two variables. So actually, this is the next topic. I think this is chapter 14.5 in our textbook. If you look at this chapter in our textbook, so the author starts to discuss a more simplified situation and then looks at a more and more general situation. So our goal is to find something like if we have a function of one variable. We proved last semester that if you have another function, so if x is a function g of t, then you have the following rule to get the derivative of the composite function if you plug in this function into this one. So the rule can be memorized very easily because it's kind of, you look at this as a fraction, and the only thing what you do is you multiply a numerator and denominator with dx. Of course, it's not precise, but this is the rule which we proved last semester, and of course we have used this rule already many times. So this is the so-called chain rule. Now, what we want to do now is we want to find a similar rule or a similar law for functions of two variables. Maybe if you I don't know whether you remember the proof of this rule here, the chain rule, for a function of one variable. I showed you the proof last semester. So it's kind of, you could imagine that, okay, you write this as the limit, and then the only thing which you have to do is you have to multiply with something. But this was not enough. So last semester, I proved this rule here by using something which is similar to this here, but for a function of one variable. So if you don't remember it, you can of course take a look in your textbook, and you will find that in order to prove this, or the way we have proved this last semester is using something like which is kind of similar to this definition here for differentiability. Now, so here in this situation for the chain rule of a function of two variables, we will see that the proof is much more easy because the definition already uses this, what we had to prove here in this situation in order to prove the chain rule. Okay, so the first situation which we want to consider is we have a function of two variables, and x and y are both functions of a single variable t. X is a g of t, and y is h of t. Okay, so we look at the function. We have a new function, which is a function of t, where we plug in. So we have here g of t and here h of t. And what we are interested in is the derivative of z. Now z is just a function of t. The normal derivative of z with respect to t. Now, the chain rule for functions of two variables is, okay, you have to, of course, you have to assume that all those functions here are differentiable. Then what we want to show is that this function here is differentiable as well. And the derivative can be obtained as follows. So you compute here the partial derivative of f with respect to x times dx over dt, plus, and then the partial derivative of f with respect to y times dy over dt. Okay, so this is the result. Now, so why is this true? Actually, the proof here is much easier than the proof we have seen last semester, because the reason is the definition here of this function here, of differentiability of this function here. Okay, so because we know that this function is differentiable, so we know we can write this function as okay, the partial derivative of f with respect to x times delta x plus the partial derivative of f with respect to y times delta y plus, and then the function epsilon 1, which depends on delta x and delta y, times delta x plus, and the function epsilon 2 times delta y. Now, this here is by definition the, we look at the fraction delta z over delta t, and let's t tend to 0. Okay, so what we do is we divide everything by delta t. Then what we obtain is, okay, delta z over delta t is equal to, so we have here the partial derivative of f with respect to x, and then we have here delta x over delta t plus the partial derivative of f with respect to y, delta y over delta t plus, and here we have epsilon 1, and we have delta x over delta t plus epsilon 2 delta y over delta t. And now things are pretty easy. If we let delta t tend to 0, you see this here will tend to this here. Then as delta t tends to to 0, this here will tend to the derivative of x with respect to t. We have this factor here, and this here will tend also to the derivative of y with respect to t. And this here will tend to the derivative of x with respect to t. This will tend to the derivative of y with respect to t. So we just have to look at those two here, because it's not that we know that as delta x and delta y tends to 0, 0, epsilon 1 and epsilon 2 both tend to 0, but we let delta t tend to 0. Okay, but you see that. So what is delta x and delta y? I write this here. So delta x is equal to, because x is g of t, so what we have here is g of t plus delta t minus g of t, and delta y is h of t plus delta t minus h of t. And as delta t tends to 0, this here tends to 0. Okay, because we assume that g is differentiable, so g must be continuous. So because of the continuous property, we know that this here tends to 0 and this tends to 0 as well. But if those two tend to 0, then those two tend to 0. So we get 0 here and 0 here. Okay, and this already implies the rule. You see, the proof is very easy here in this situation, because we have this this definition here, okay, of the of a function of two variables being differentiable. Okay, so the function is of two variables is differentiable if you have something like this here, and this makes the proof very easy. Okay, so this is the chain rule for a function of two variables. So you have something similar to this rule here. You see here you can still think about fractions, okay, because you can kind of erase this one and you get equality, but this doesn't work here anymore. Okay, if you erase this, you would get df over dt twice. Okay, it's here only once. Okay, so here the similarity with fractions breaks down if you go from 1 dimension to 2 dimensions. Okay. Now, so this is I think the textbook calls this the chain rule version 1 or something like this. Now there is also a version 2 or second case. So for the second case, we consider a slightly different situation. So for the second case, so this is what I think the textbook calls this chain rule. Case 1 or case 1. For the case 2, we consider a slightly different situation. Again, we have a function of two variables. But now, what we plug in for x and y are also functions of two variables. So x is a function, let's say, g of s and t, and y is a function h s of t Okay, so we plug in. What we then have is here for this we do not have only a function of one variable. We have a function of two variables. But again, we assume that they are all differentiable. Okay, then if I define a new function, okay, so I have my f and I plug in the two functions, then this function is differentiable as well. Now it's a function of two variables. And oh no, this is not true. The partial derivatives exist. Sorry. Now under this assumption it's okay. So, but this actually is, I think this doesn't is not proved in the textbook. So the only thing which is interesting for us are the partial derivatives. So the partial derivative of z with respect to s is equal to, now actually this second case already follows from the first case, because if you want to compute this partial derivative, then what you do is you consider t as a constant, so actually you are already in the first situation. Okay, so you have, by the first case, you have the partial derivative of f with respect to x times the partial derivative of x with respect to s plus, and then the partial derivative of f with respect to y times the partial derivative of y with respect to s. And for the partial derivative of z with respect to t, the same. So you have the partial derivative of f with respect to x times the partial derivative of x with respect to t plus the partial derivative of f with respect to y times the partial derivative of y with respect to t. Okay, so actually this second case, what our textbook calls the second case, is already included. It's just a special case of the first case, because if you compute once more, if you compute these partial derivatives here, anyway, you consider this function as a function of s, where t is a constant, and for this situation, you are just in the first case, and you can apply the first case in order to find the derivative. Okay, so this is the chain rule for functions of two variables. Maybe let's just look at a simple example. So for instance, if this is our function z, and we have a x which is 3 times d plus s, and we have a y which is e to the 2st. Okay, so let's just look at one example to see how to apply this. So if I want to compute the partial derivative of z with respect to, let's say, it doesn't matter, with respect to s. Okay, so by the rule, I have to compute the partial derivative of z with respect to x times the partial derivative of x with respect to s, plus, and then the partial derivative of z with respect to y times the partial derivative of y with respect to s. Okay, so this is now easy computation. So the partial derivative with respect to x, so this will cancel out. So what I have is 2x plus y times, and then the partial derivative of x with respect to s, which would be equal to 3 plus, and here the partial derivative of z with respect to y is x plus 2y, and here the partial derivative now of y with respect to s. So what you get is, here you have to use the chain rule, so e to the 2st times the inner derivative is 2 times t. Okay, and similar for the partial derivative of z with respect to t. Now, all those calculus textbooks give a rule how to memorize this formula. Now, you see that the independent variables which we have here are t and s, and the dependent variable is actually z, and these x and y here are intermediate variables. So what you have to do is, if you have to compute the partial derivative of z with respect to s, is you compute the partial derivative with respect to every intermediate variable, and so every intermediate variable will give you an addend here, a term here in this sum, and then you have to differentiate the intermediate variable with respect to the variable where you are interested in. This is one way to see it. The other way, which is which you also find in our textbook, I have to say honestly, I don't think it's very useful, but I don't know why all those textbooks emphasize make a diagram. Okay, so let's make a diagram. I think the rule is easy enough, but okay, if you haven't done it very often, then maybe this might be helpful. So you have here this kind of situation. Now you write the partial derivative to all of those lines. You can see this as a graph, so to all the edges. So you have here the partial derivative of z with respect to y. Here you have the partial derivative of x with respect to t. Here you have the partial derivative of x with respect to s. Here you have the partial derivative of y with respect to t. Here you have the partial derivative of y with respect to s. And then if you are interested in like, so here we are interested in the partial derivative of z with respect to s. So what you do is you look where is s. So here you have an s, and here you have an s. And then you multiply along the path, and you add over the all the passes you have, and you get the rule. Okay, so I don't know why all those textbooks emphasize this rule here. Maybe you will find it helpful. Honestly, I don't think it's helpful. At least for me, it's not helpful. It's, because the rule is easy enough to memorize. Okay, so maybe let's do. Sometimes it's quite easy to get confused. Okay, because sometimes you have many variables, and here for this situation, for the second case, we have only 2 independent variables and 2 intermediate variables. But of course, if you have more, you have a similar rule. And if you have too many variables, you might get confused easily. Then this might still be useful if you like such things. Okay, so for instance, this example here. This just shows you that sometimes you have to be careful, because sometimes it's quite easy to get confused. So here, this is one example. So x is equal to r squared plus s squared, and y is equal to 2rs. Okay, so we have this situation, and what you should compute is the partial derivative, the second partial derivative of z with respect to r squared. Okay, so this is not very complicated. So what we assume, of course, is that this function is differentiable. Otherwise, we cannot use our rule. So we have to assume that the function f of x, y is a differentiable function. Now, so what we have to compute first is this partial derivative with respect to r. So by the chain rule, we see the intermediate variables are x and y. So we have a term for every intermediate variable. So we take the partial derivative of z with respect to x times the partial derivative of x with respect to r, which is 2r, plus, and then the partial derivative of z with respect to y, and then the partial derivative of y with respect to r, which is 2s. Okay, and then we take the derivative of this one here. But you have to be careful, because of course this is also a function now of r and s, and also this is a function of r and s of 2 variables. Okay, so if you take the second derivative, or if you take the derivative once more with respect to r of this function here, of course this is a function of 2 variables, okay, r and s. Then for this term here, so we take the derivative with respect to r. Okay, you have to use the chain rule. So the easy part is, okay, take the derivative here with respect to r. So what you get is 2 times the partial derivative of z with respect to x, plus, and then you have 2 times r times the partial derivative with respect to r of the partial derivative of z with respect to x, plus. And here the same, but because this does not depend on r, so we have just 2s, and then the partial derivative with respect to r of the partial derivative of z with respect to y. Okay, and for those two here, we have to use the chain rule again. Okay, because this is a function of r and s, two variables. So, and we compute the partial derivative with respect to r. So again, we have here two intermediate variables, x and y. Okay, so we have to use chain rule here once more. So we have 2 times the partial derivative of z with respect to x plus 2 times r. Now for this one, okay, so we take the partial derivative of this with respect to x. So what we get is the second partial derivative with respect to x times, and then we have again the partial derivative of x with respect to r, which is 2r, plus, and then the partial derivative with respect to y. Under certain assumptions for f, the order does not play any role. Okay, so I write here partial derivative of x, partial derivative of y, and then the partial derivative of y with respect to r, which is 2s, plus, and then we have also here plus 2s, and then here we have to do the same. So we have the partial derivative of z with respect to x times the partial derivative of x with respect to r, which is 2r, plus, and then the partial derivative of z with respect to this. So this is the second partial derivative with respect to y times the partial derivative of y with respect to r, which is times 2s. Okay, and then you simplify it, and that's it. So you see, sometimes you have to be a little bit careful taking partial derivatives. Of course, you have more, because if you have more variables, you have more things to think about. So sometimes it's easy to get confused. But you just have to do it slowly, and it's not very complicated. Of course, you have also a general chain rule. Which includes all the previous cases, and actually I could have stated the general chain rule right from the beginning, but maybe a little bit more confusing because it contains much more variables. So we have n intermediate variables, and every intermediate variable is a function, let's say chi of, let's say, m variables. Okay, then if you plug this into the expression here, then what u becomes a function of m variables. And you might be interested in the partial derivative of u with respect to some of the t1 up to tm. So let's say tj. Okay. Now, so the rule is always the same. So you have to compute partial derivative with respect to every intermediate variable. So first with respect to x1, and then the partial derivative of x1 or g1 with respect to tj, plus, and then you go on the partial derivative with respect to u with respect to x2 times the derivative of x2 with respect to tj, plus, and so on, plus the partial derivative of u with respect to xn times the partial derivative of xn. And you can, of course, you can plot the same diagram if you are the visual type and you need a diagram for doing computations. Okay, plot a diagram. Okay, but the rule is once more easily memorized. You just have to add a term. You have a term for every intermediate variables. So you have to identify the intermediate variables, and then you have just one term for every intermediate variable, and you have to take the partial derivative first with respect to the intermediate variable, and then the intermediate variable with respect to the variable where the partial derivative is sought. Is it necessary to do an example here, or I guess you have seen this maybe in other classes, partial derivatives, and you might have computed already many. So I don't want that you get bored by seeing me doing easy examples. We will do some examples in the assignments. I think this is not very complicated because essentially it's just taking derivatives, something which we have done already last semester. Now, this is a good time to take once more a look at implicit differentiation. So this is one of the techniques which we have learned last semester. But maybe you remember last semester, or maybe you don't remember. I emphasized last semester that actually we have used the method of implicit differentiation already many times, but actually we have never really justified that we are allowed to use the method. And I briefly told you last semester the reason why we haven't justified it last semester is because the justification is complicated. There is a complicated or a deep theorem behind it. Now, this is a good time to go back to the method of implicit differentiation and to take once more a look at it. Of course, we are still not able to justify the method, but we can at least see it now in a different light. Okay, so implicit differentiation. You know what the method is. So, for instance, if you have this example here, okay, then this will give you. In this case, you can even solve for y and you get an explicit function, but you can interpret this as a function which is implicitly given by this equation. And as we have noted last semester, you don't really have to solve for y. You just take the derivative on the left and the right-hand side, and then you compute the derivative. Okay, but maybe. So what is the problem with the method? So most of the time you apply implicit differentiation if you're not able to solve for y. Okay, so the method is most of the time applied for such a situation. If you can solve for y, for instance, here of course it's not so convenient to solve. It's not very complicated here, but it's not so convenient to take the derivative of the solution here. It's much more easier to just use the method here. Okay, so sometimes even if you can solve, okay, we still use the method of implicit differentiation, like in this example here, because it's more convenient. But the real strength of the method is that even if you cannot solve for y, then you can still use the method. Now, what you clearly need is so in general you have given a function of two variables. So you have given something like this here. Equal to c, is it equal to 0? Okay, so you have given an equation like this. You just put you just take the one on the other side. Okay, so you have given an equation like this. Normally you cannot solve for y, okay, and you want to find the derivative of y. Now, what is the problem? What is the problem of the method of implicit differentiation? Of course, it's easy to apply the method. Okay, you take the derivative on the left-hand side and right-hand side and compute and solve for the derivative. Okay, but actually, before you do this, okay, or even so, if you get an answer, okay, you do not know whether the answer is meaningful because you do not know whether this really defines a function y is equal to y of x, and whether this function is really differentiable. And normally you cannot solve for y. Okay, so how to see just from the equation that such an equation defines a function implicitly. So y is equal to y of x. There is a function which solves this, and the function is differentiable. Okay, this is the main problem in using the method. Now, if you know this already, okay, if you know already that there is a function y is equal to y of x which satisfies this equation, and y is differentiable, so assume we know that there exists a differentiable function y is equal to y of x with okay, so assume this. Assume we know this. Okay, you see here what the main question is. The main question is how should I know this? Okay, because if normally if I apply the method of implicit differentiation, I cannot solve for y. That's why I use this method. Okay, so but still I have to know this before I use the method. Okay, but if we assume that okay we know that there is a function in this situation, of course we know it because we could solve that there is a function which is differentiable. And if you know that f is differentiable as a function of two variables, moreover, assume that this function is differentiable in our new sense, which we have defined last semester, which we have defined last time. Okay, then so this means that okay, so this is differentiable here. This function is differentiable, and this means we can use here the chain rule in order to take the derivative. So for the derivative, what we get is if we use the chain rule here, so the partial derivative of f with respect to x, then actually we have the partial derivative of x with respect to x, but this is 1. Okay, so maybe I don't write this. So plus, and then the partial derivative of f with respect to y times, and then the derivative of y with respect to x must be equal to 0. So we see that we can easily get an expression for the derivative. Okay, so that if we know there exists a function which satisfies this equation here, okay, and we know that the function is differentiable, and we know that f is differentiable, then the derivative is given here by this expression. This is something we get here now from the. That's why I said let's take once more a look at implicit differentiation, because we can use now the chain rule for a function of two variables to easily find the derivative for this general situation here. Okay, but you should realize, okay, the problem. This is not a problem. Okay, this is easy to check. For instance, okay, I give you this function. It's easy to check that this function is differentiable, but the real problem of the method is okay. How should we check this here? In particular, in the cases where we cannot solve for y, okay, how should we check this here? Now, there is a very, very deep theorem in mathematics which is called the implicit function theorem, and this theorem tells you that under which conditions you are allowed to use the method of implicit differentiation. And actually, the conditions are very easy. Of course, the conditions should be checkable in terms of the function f. So all conditions should be related to the function f. Now, the conditions which we need is, you find this in our textbook. If you have a point, here we are two-dimensional. So if you have a point AB, okay, and you have that this point is a solution, okay, of this equation here. So f of AB is equal to 0. You have that in a neighborhood, so something like this here. In a neighborhood around AB, this function here is differentiable. You have that the partial derivative with respect to y at this point is not equal to 0. This is what you need here. Otherwise, this doesn't make sense. And so all those conditions, you would guess them because this is what you need. Actually, this makes sense. Plus, if you know that the partial derivatives with respect to x and with respect to y are both continuous inside this neighborhood, then it can be proved that you can solve this equation locally around AB. Okay, so you can find the function y is equal to y of x, which satisfies the equation and is differentiable, and the derivative is given by this here. Okay, so this you find this in our textbook. So these are the conditions which are under which the implicit function theorem holds, or in other words, these are the conditions under which you can use the method, which you are allowed to use the method of implicit differentiation. And this is maybe a result. I'm not sure whether you will learn it, because this is actually looks quite innocent, but it's quite quite deep result in mathematics, and the proof is also not that easy of this result. So you need quite a lot of tools which you haven't learned yet in order to prove this. But the main thing for us is that using the chain rule, okay, you can because we still for us the method of implicit differentiation still largely is formal. Okay, so every time we see something like an expression like this here, we just apply it. Okay, and when more or less the implicit function theorem tells you whenever the expression you get makes sense. Okay, you can more or less under this condition you can do it. Okay, this is what you can apply the method of implicit differentiation. This is what the implicit function theorem tells you. But for us, we will still largely apply it. But you see, for instance, that in this situation, okay, what you have is if you plot the graph, this looks more or less like a circle, but a little bit fatter around so here and here. Okay, so you have something like it's sometimes called a fat circle. Okay, so it's like if you have x squared plus y squared is equal to 1, you would have a circle, but this circle is a little bit. So here is not so curved. Here also not so curved, and here. And you see that because you see that 1 point, if you have a solution, okay, so you see that the solutions of this equation, okay, are exactly what I have drawn here, okay. But you see that for this point here, okay, you have a problem because the partial derivative of f with respect to y, which is 4 y to the cube, is equal to 0 here at this point. Okay. So these are the only points where you cannot solve. The implicit function theorem tells you here for these 2 points you cannot solve locally for y. Okay. For all other points you can do it, but this doesn't cause any problems for this here because you just you see here. Of course, you have the problem if you look at it as if you want y as a function of x, but if you just reverse it, if you want x as a function of y, you don't have this problem anymore. So actually, also for this, you can locally apply the method of implicit differentiation. Okay, but this the important thing is that the chain rule gives you an easy method to for a general situation to compute the partial derivative. So, for instance, in this case, you get so the function here in this case is x to the 4 plus y to the 4 minus 1. So the derivative with respect to x is equal to the derivative with respect to the partial derivative of f with respect to x, which is 4x to the cube, over the partial derivative of f with respect to y, which is 4y over cube. Okay, and this is an expression which is valid unless if you exclude those 2 points here. Okay, but you see also for those 2 points, kind of still true because this will be infinity and the slope of the tangent will be infinity as well. Okay, so but this should not be new for you because also last semester I told you that implicit differentiation is not so innocent. Okay, it's not so. It's a method which is easy to use, but not easy to justify. Okay, not so easy to justify. And until now, you should be aware of this. We have largely used the method without justification of the method. So we have just applied it. This maybe a method you have seen even in high school, but in high school maybe nobody told you that you have even that you have to check something before you are allowed to use the method. And in some situations it's not possible to use this method. But because if you look at the implicit function theorem as formulated in our textbook, the range the range where you can use the implicit differentiation this method is rather huge because every time this does not make sense, you know, okay, you cannot use it. This is quite natural, the natural range. Now, of course, you have something similar for functions of 3 variables, or I should put it different. You have a equation in 3 variables which gives you which implicitly defines a function of 2 variables. So you have something like this here. You have an equation like this here which defines z as a function of x and y. So I assume that this equation implicitly defines z as a function of x and y. Moreover, you need some assumption. Under some additional assumptions, you can, for instance, compute the. You can use this here to compute the partial derivative of. So maybe I should say what do you need? For instance, assumptions which are sufficient are you can solve. So you have the first thing you need is such a function exists. So this really gives you implicitly defines a function of x and y, and you have to assume that this function here is differentiable. And you have to assume that also this function here is differentiable now as a function of 3 variables. Then you can apply the chain rule, and what you get is, okay, you have the partial derivative of f. For instance, if, I should say, what are we interested in? We are interested in the partial derivative of z with respect to x. So if we are interested in this partial derivative, we have to differentiate here everything with respect to x. You shouldn't be confused that x is now an intermediate variable and x is the variable we are interested in. So you have the partial derivative of f with respect to x times, and then you again have the partial derivative of x with respect to x, which is equal to 1, plus the next term would be the partial derivative of f with respect to y, but you have the partial derivative of y with respect to x, which is 0, and then you have the partial derivative of f with respect to z times the partial derivative of z with respect to x is equal to 0. Okay, so you get that the partial derivative of z with respect to x is equal to, so you have minus, and then fx over fz. And similar, you get that the partial derivative of z with respect to y is equal to minus fy over fz. Okay, so you can use the chain rule in order to get the partial derivatives here for a function which is for a function of 2 variables, which is implicitly given by an equation. And again, the main thing is, okay, again, this method is can be justified for in many situations, and also for this situation you have an implicit function theorem. So also for this situation you have some easy checkable assumptions for the given f, which tells you under this assumption you can solve here for z at least locally, and the solution is differentiable, and the derivatives of the solutions are given by those 2 expressions here. Okay, you find some examples in our textbook. More or less, the way how we use the method of implicit differentiation does not change. Okay, so we have given such an equation, and we just apply differentiation on the right and the left-hand side. Okay, the only reason why we revisit here the method of implicit differentiation is because given a general equation, we can now use the chain rule in order to write down expressions for the partial derivatives. Okay, so any questions to this? Now, if not, then we can start to define derivatives in different directions, not only with respect to x and with respect to y, which are given by the partial derivatives. So this is the aim of the lecture today. Which this is what I told you at the beginning of the lecture. And for this, we take a look at because I'm quite unable to draw such things. And now, since we are talking about things in the space getting more and more complicated, so I will show you this. This is not what I wanted to show you. This also not. This is not what I wanted to show you. This is, by the way, maybe you saw this. I'm not sure whether I assigned this problem as homework. No? This is quite nice. This is a little bit. This is not related to what I want to talk after this. But so this is something, because for this homework we had one example where you had a plot of the level curves, and you had to find out are certain partial derivatives or mixed partial derivatives positive or negative. Such examples are quite nice because they give you some insight in the behavior of partial derivatives. Now this is an example of a similar type, and actually this was an example which I think appeared in one of the previous Hoikaus. So this is a quite nice example. You have three plots of a function, and one of them is f, one of them is the partial derivative with respect to x, and one is the partial derivative with respect to y. And you have to figure out which one is which one. Okay, so one is f, one is fx, one is fy, and you have to figure out which one is which one. Maybe you can take a few minutes and think about this. This is a quite nice exercise. You see, it's not so easy. You still have to think. If you haven't seen the exercise before, it's not so easy. You still have to think a little bit about it. But it's quite a good exercise for getting a feeling for partial derivatives. It's much better exercise than just giving you a function and computing the partial derivatives. It's boring. So who has an answer, and who can tell me why? So which one is f? Which one is A? Yes, correct. Because for instance, if you look at okay, so this is f here. So if we assume that this is f, then if you look at the partial derivative with respect to x, so you see that you have actually, because you look at this direction here, so there is a change in the behavior roughly here, okay? Because here you have first decreasing. So if you first decreasing, and then here you have increasing, and if you move here, then you have for this range you have increasing, here you have decreasing. So this means that once you have identified this here as f, things are getting very simple, because you know that if you look at this direction x, you know that here you have something like you have just one change in the behavior, okay, and this should be this one and not this one, so it's very easy. So you see that the derivative of f with respect to x then should be this one, and okay, then the final one should be this one. You don't have to check it anymore. So you have just to, once you have figured out which one is f, okay, you have it's very easy to figure out, okay, which one of those two is the partial derivative of f with respect to x, and which one the partial derivative of f with respect to y. So the main thing, of course, is to figure out which one is f, okay, and for this one you have to try every one, and you have to exclude the other ones if you fix the other ones. So you see, actually, such an exercise, maybe if you do it for the first time, it's not so easy. And if you have it in the Hoikau and you have just 5 minutes time for such an exercise, of course, it's a little bit. It's not so it's not such an easy exercise. And I remember when we chose this exercise for the Hoikau, not many students got the answer right. I think less than 20% of the students. I can understand why, but this is a very good exercise because it helps you to understand. It helps it helps you to understand better partial derivatives, and it helps me to understand whether you understand it. Okay, if I give you a function and you compute the derivative, this is easy. Okay, also the computer can do it, but to give this to Maple is not able to check which one is which one. For this, you really have to understand the definition of derivatives. Okay, so any questions to this? So these are quite good exercises, and such exercises, of course, because they are quite good exercises and they check your understanding, such exercises often occur in the Heu-Cow. So this is this one. Okay, so what we want to do is we want to kind of generalize the definition of the partial derivatives. So what we have is, we assume we have given a function of two variables, x and y. Then what we do now is we fix a direction. You see here given by this vector u here. So u is a unit vector. Now, what we do is we look at the plane which passes through u, and we fix a point actually on the surface. You see this blue surface is the surface given here by this function of two variables. So the graph, kind of the graph of this, or the graph of this function. This is the surface S. We fix a point on the surface which is called P. We fix a unit vector, and we look at the plane which is perpendicular to the xy plane, which passes through the unit vector, or which has the direction, I should say, of the unit vector, and which passes through a point P. Now, this plane here will give a curve of intersection, which is here denoted by C. So C is the curve of intersection of the graph of f with the plane in direction of u perpendicular to the xy plane and through the point P. So this is this curve here which you see C. Now what we wanna know is, okay, what is the slope of the tangent to C at the point P? Okay, so this kind of this is a generalization of the partial derivatives, because for partial derivatives we look at the vector u, which is a vector either in direction of the y-axis or of the x-axis. Now, of course, this slope is quite easy to compute. You fix on the curve C another point, call it Q, and what you do is you project this point, the P and the Q, both points you project down onto the xy plane. So this is what you see here. So you have a P prime and a Q prime, which is just a projection of P and Q onto the xy plane. Okay, so this is what you have here. And because of the construction of C, the projection of those 2 points, so the vector pointing from P prime to Q prime, okay, must be a multiple of u. Okay, so let's say Q is any point on C. So let's say the coordinates are given by x, y, and z. Now, if you project it down, so P prime and Q prime projections onto the xy plane of P and Q, then of course the vector from p prime to q prime must be a multiple of the unit vector u. Okay, and this of course is the vector which is given by x minus x0, y minus y0. This is now in the plane. So you see from this that okay, the x must be equal to, let's say I didn't say what u. Let's assume that u is equal to ab. Then x must be equal to x0 plus hu, and the y must be equal to y0 plus p times h. Okay, so if you want to know the slope of the tangent you see here, so the slope of the tangent to C at the point P, then okay, you have the limit h tends to 0, because this here describes actually the curve. So you have f of x0 plus ha, y0 plus hb minus f of x0 y0 over h. And this is called the directional derivative of our function f at the point x0 y0 in direction of u. Okay, so this is called directional derivative at x0 y0 in direction of u. Okay, so maybe I can add here x0 y0. Okay, so this is the so-called directional derivative. I should stress here already, it's very important that u is a unit vector. This is very important here, because otherwise this definition would depend on the length of u. Okay, and this wouldn't make sense, because you would get for different lengths of u, you would get a different value. But what you want to have is that what we define here is a measure at the point P of the, if you go in direction of u, okay, what is the rate of change? This is what you want to have. This is also the interpretation of this quantity here. No, actually, sorry, what I said was wrong. Here you cannot. Here you don't see this, because. But in a moment, this becomes important in a moment. Okay, sorry. So here it's not so. It's not apparent why u must be unit vector. Of course, you can make the same definition for also other vectors. Now. So the first thing we want to do is, okay, we want to know how to compute in a more convenient way the directional derivative. Now, what we of course would expect, or what we of course expect, is that whenever f is a differentiable function, then all derivatives in all directions should exist. Okay, and they may be also easy to compute in this case, and this is really the case. So this is the next theorem in our textbook, which tells you that if f is differentiable, then all the directional derivatives exist and can be computed quite easily. Okay, so this is the following result. Assume that f is differentiable. Then exist for all unit vectors u, and it can be computed very easily as follows. So you compute the partial derivative of f with respect to x times a, times a plus the partial derivative of f with respect to y times b, where u is the unit vector given by a and b. Now, the proof of this result actually is just a chain rule, okay? Because you see that by the definition of the directional derivative, maybe let's fix a point. Or it's not so important to fix a point. So we have the limit h tends to 0, and then we have f of x plus ha y plus hb minus f of x y over h. So actually, what you do is you look at this you look at the derivative of the function f, and then you have x plus ha y plus hb at h is equal to 0, where x and y are now given constants. Okay, so by the chain rule, okay, so this is nothing else but the partial derivative of f with respect to x, evaluated at h is equal to 0, so at xy times, and then the derivative of this function here with respect to h, which is a, plus, and now the partial derivative of f with respect to y. You should observe here, so maybe it would be better to write here x0 and y0, because this partial derivative is not with respect to this x here. This is with respect to this coordinate, okay? Because this is the intermediate variable, okay? So maybe it's more clearer if you write here x0, y0. This is sometimes the confusing part, okay? Because in applying the chain rule, so you should be a little bit careful here, okay? Because what I have to write here is the partial derivative with respect to the intermediate variables, okay? And maybe you have the function which you plug in also depends on x and y, okay? So, but this what I have here is the partial derivative of f with respect to this variable, and then evaluated at the point where you have h is equal to 0, so at x0, y0 in this case. Okay, so they are both evaluated at x0, y0 times b. Okay, and this already proves the result. You see that because of this, easy formula which you have here, okay, we use a notation which you might have seen already in other classes. So for because we can write this here as an inner product of this vector here with this vector. Okay, and for this inner product, you might know for this vector, you might know we have a special notation. So this is called the gradient of f. Okay, so one of the ways to define the gradient is okay, because you see that if f is differentiable, computing directional derivatives is possible by using this formula here. So and this formula becomes more simple if you use this notation here. So it's in this situation it's just a notation. Okay, so but we will later on we will see that actually this vector has a couple of quite interesting properties, and this will be another reason why we are interested in this vector here. Okay, so maybe let's look at an easy example. So for instance, assume you have given this function here. So why do I call it? Let's call this f. I'm not sure why. I don't know why I call this. Okay, so this function. Let's say the point x0, y0 is equal to 2, 0. So this is the point where we look at the behavior of the function with respect to the rate of change, and we want to look in. We want to look towards this direction here. Okay, so actually what this means is, okay, you are on this function, so this will give you a surface. You are on this function, okay, you are standing at this point here on the function, and you are interested in, okay, if you walk in this direction, okay, what is the rate of change, okay, of the function, okay? So you can kind of imagine this like you are standing at this point here, and you walk in a specific direction, and you want to know, okay, how steep is the curve there if you walk in this direction. Now, one important thing is, as I have mentioned already, that u is a unit vector. Okay, for a unit vector, you have this formula. So whenever you have such an exercise, okay, you have to replace v by the unit vector in the same direction. So what you have here is 1 over square root of 2i plus 1 over square root of j. But then, of course, the computation becomes trivial. So you compute the gradient of f, which is the vector given by, so the partial derivative with respect to x is 2x e to the y, and the partial derivative with respect to y is x squared e to the y. So we are interested in the gradient at the point xy is equal to x0, y0. Maybe I shouldn't write it like this because this is just a function. So the gradient of f at x0, y0 is equal to, so y is equal to 0, so you get here always 1. So what you have is 4 and 4. And then you can compute the directional derivative in direction of u of f of x0, y0 as the inner product of 4, 4 with this vector here. So 1 over square root of 2 and 1 over square root of 2. So what you get is 8 over square root of 2. Or if you like, 4 square root of 2. Okay, so you see that from this example, you see that because this function, of course, is differentiable, so I don't have to check this, so I can use this formula. Okay. Interesting question is, okay, whether or not if you have a function, okay, such that the directional derivative in every direction exists, okay, does this already imply that the function is differentiable? It's kind of because you have we saw already it's not enough if the partial derivative with respect to x and the partial derivative with respect to y exist. Okay, it's not enough for a function being differentiable. Okay, we saw already some counterexamples. Okay, so you might once you define the directional derivative, you might believe that okay, the existence of all the directional derivatives, okay, in a point should imply that the function is differentiable. Now, this is not the case. Next time I will show you an example. So it's not true. Even if the directional derivative of a function in every direction exists, okay, it still does not imply that the function is differentiable. The reason is because you see that directional derivatives are more or less just defined by walking along a line. Okay, because I mean, if you look at the surface, you do not walk along the line, but if you look at the direction in which you look, okay, you just you walk in the direction of a line if you project the surface down on the xy plane. Okay, and we saw already for limits of functions of two variables that if you approach, for instance, 0, 0, okay, along lines, okay, and the limit always exists and is equal to 0. This does not. The limit exists and is always the same. This does not imply that the limit exists. Okay, but because the path at which you approach 0 could be much more complicated than just a line. And this is more or less also the reason why the existence of all the directional derivatives does not necessarily imply that the function is differentiable. I will show you next time an example which demonstrates this. Okay, because I know in one of the previous Hoik-Haus, this was also one of the multiple choice questions, and one of the choices was if the directional derivative exists in every direction, then the function is differentiable. Is it true or wrong? Okay, and the answer was wrong. And this was maybe it's a quite tricky multiple choice question, because it's not so easy to, it's not so complicated either, but it's not so, you have to think a little bit to come up with an example of a function where all the directional derivatives exist, but the function is still not differentiable. Actually, we have already seen such an example. Okay, I will show you this next time.